So it's my pleasure today to introduce Susan Murphy as the 2020 H.O. Hartley Memorial Lecturer. And I guess as everyone realizes, it's now 2021, so we had to postpone this for a year. But it's great that we're able to do that. And we really appreciate that Susan's been able to join us from Massachusetts today. I guess between hockey games. So let me just say a few words about Susan before we get started. So Susan is the Mallinckrodt Professor of Statistics and Computer Science at Harvard University, and is also a Radcliffe Alumni Professor at the Radcliffe Institute at Harvard. Professor Murphy's research focuses on improving sequential, individualized decision-making in health. More specifically, she has pioneered clinical trial designs that utilize just-in-time adaptive interventions. She has also developed micro-randomized trials, and these trial designs have been used in a broad range of health-related interventions. Among her many awards, Professor Murphy is a member of the National Academy of Science and the National Academy of Medicine. In 2013, she was awarded a MacArthur Fellowship for her research on experimental designs to inform sequential decision-making. She is a past president of the Institute of Mathematical Statistics and Bernoulli Society and former editor of the Annals of Statistics. Before Susan begins her lecture, I would like to say a few words about the H.O. Hartley Memorial Lecture. So Jim, I think you knew Dr. Hartley? Anyone else here from that time? Perhaps not. Okay. So the Hartley Memorial Lectures were established by the Texas A&M University Department of Statistics in 1988 to honor the memory of Herman Otto Hartley. Dr. Hartley accepted an appointment as a distinguished professor at Texas A&M University in 1963 and subsequently founded the Institute of Statistics. He served as its director until his retirement in 1977. Hartley built his initial faculty of 4 into a group of 16, directed more than 30 graduate students, and published over 75 papers during this period. He served as the president of the ASA in 1979 and died, unfortunately, in December of 1980. Dr. Hartley is well known for his work on the foundations of sampling theory and made important contributions to mathematical optimization, estimation of incomplete data, estimation of variance components, and establishment of safe doses in carcinogenic experiments. He collaborated with Egan Pearson to produce the classic 2-volume biometric tables for statisticians. Hartley was deeply committed to all phases of his profession, including education, research, and advising users of statistics. He was not only a brilliant statistician, but a warm and caring human being. His legacy continues to have a profound influence on Texas A&M students and the larger statistical community. So it is now my honor to invite Dr. Murphy to provide a lecture entitled "We Use RL but Careful." So thank you.
Okay. It's great to be here with all of you. So this talk is, it's mainly, the reason why we undertook this work, and we're still involved in this work, is to prevent misleading statements. It's very easy when you work in the field of AI. I mean, many people who work in the field of AI know that we've had quite a few disasters, and we don't want to do that. We want to really communicate with precision, and you'll see our efforts in that direction here. First, I want to say a few words. I don't want to just repeat what Val said. What was impressive, like when I went to his background, it's just amazing. You look at these guys who are part of that generation, and they work across this entire field, and they make fundamental contributions from one field after another. And they're not only just doing theory, they're doing real application. And he was that type of a person. It's incredibly impressive. I think it's something that we need to aspire to be more like these kinds of people. So it's an honor. Thank you for inviting me. The kind of work I do, it's big science. There's a lot of collaborators. There's computer scientists on here, human computer interaction specialists, behavioral scientists, statisticians, app developers. All of these individuals come together to do the kinds of studies and the work that I'm involved with. It's because of them I can do that work. So what I'll do is I'll start off with one of the little icons. The icon in the center of the first slide was about heart steps. And I'll use heart steps to illustrate all the ideas. So heart steps is a series. These studies are over now. It was a series of 3 studies, and the goal was to develop a mobile activity coach. It would provide nudges to people on their smartphone. It involved a tracker, a commercial tracker as well. And there were 3, as I said, there were 3 studies. They were all micro-randomized. I'll make that clear as I go through the talk. And the second 2 studies, the 3-month and the 9-month study, were personalized. And I hope to make that clear too as I go through. So like all mobile interventions, all digital interventions, all of them have multiple components, multiple intervention components, all working in their own way. I'm going to focus on only one intervention component here, and that's whether or not one should send a suggestion around at any of 5 times a day. These 5 times are user-specific times. They're related to your perception of your morning, your perception of your midday, and so on. They're approximately every 2 to 2.5 hours. So at any one of these times, one could get a notification. The content of the notification is tailored to the sensor data that was available at that time. In particular, whether you are at home, work, or at the office, what the weather was like right now, the time of the day. This one I received early in the morning. It was a pretty cold day. So it's attempting to get me to reframe and go out and walk to work. And for our purposes, we're going to focus on whether or not the software should send one of these contextually tailored suggestions versus not. Each suggestion, the content is tailored to your current environment. So the effect of that content should be in near time. It's intended to impact to be actionable in the near time. And that's why the outcome here is, I think I can use this dot. The outcome is the 30-minute step count, the immediate 30-minute step count after each one of those 5 times. The micro-randomized part is the treatment action. So each of the 5 times, whether or not a suggestion is sent is randomized. So for example, in a 3-month study, you're talking about 5 times 30 times 3, many randomizations. After the study is over, you can imagine what the data would look like. It's this trajectory, 1 per individual. And each trajectory is composed of tuples. And the tuples are state, action, reward. State is all of the data that's been accruing on that individual. So it's sensor data from the smartphone and sensor data from the wearable. In this case, there was no self-report questions in this study. There were no self-report questions. Then there's the action, which is whether or not you deliver the suggestion, like I mentioned earlier. And then the reward, I also mentioned, I called it an outcome on the last slide. It's the log of the 30-minute step. I'm going to use this notation throughout. It's just the expected reward given current state and action. I'm going to denote it by a little r or SA. Like this. So I'm going to talk about the algorithm that we ran on HeartSteps V2 and V3. I'm just going to give you an overview of that algorithm because what I really want to get to is evaluation of that algorithm, whether or not it's personalized. So during this study, this algorithm selects actions. You could think of them if you want as randomizing actions. It selects actions with the goal of maximizing the sum of the rewards over the entire duration. It doesn't completely go after maximizing that sum, this physical activity. They're subject to a lot of constraints, and these certainly at the time we designed this algorithm, they're pretty ill-posed. They were ill-posed constraints. One is we had to ensure that after the study was over, we could still conduct a variety of analyses, off-policy analyses, as well as causal inference analyses. So this constraints thing, and now we have we've operationalized how one might do this, but at the time this study was designed, that wasn't the case. We also have to, from a scientific, domain science perspective, we have to manage a user burden and habituation. If you've ever downloaded an app, you know exactly what I'm talking about. So in HartStips V2, V3, what we did was we started off with a simple Thompson sampling bandit algorithm, and we generalized it to take into account the potential for burden. And you'll see, I'll give you just a highlight of how we did that. Okay, so if you're an outsider to the field of reinforcement learning, there's a useful way to think about it, particularly when it's used online. And when it's used online, there's always two elements. The first element is simply a statistical model that's implemented incrementally. That's all. It's nothing more, nothing less. It's just some statistical model incrementally implemented. So as data accrues, it updates the estimators of the parameters in that statistical model. Here, what we use is a Bayesian linear regression model. So this is nice because this is going to give us a posterior distribution. The second element of all these algorithms is some method of selecting the actions. And people mix and match these two elements all the time. It just depends on the setting. So what we're going to use is posterior sampling. So what does posterior sampling do? Posterior sampling uses, of course, the posterior distribution to decide how to select the actions. In particular, what we'll do is we calculate the posterior, so we calculate the posterior distribution of the reward in state S if you send a suggestion, minus the reward in state S if you don't send a suggestion. So it's the advantage of sending a suggestion in state S. We calculate the posterior probability that difference, that advantage, is greater than some bias term. And that bias term depends on the current state. If that posterior probability is large, that means there's a lot of evidence in favor of sending a suggestion. The posterior probability is low, there's much less evidence in favor of sending a suggestion. So the accruing data evidence is indicating that there's less evidence. So this threshold term, it was built, it was updated during V2 and V3 on each individual, but it was built primarily from HartStips V1. And what it is, if you're familiar with full RL, it's the prediction of the value of taking an action versus not taking an action on the future sequence of rewards. That's what it is. And what we did was we built that using a simple MDP kind of model. We built that on HartStips V1 off policy, and then we just used it here, updating the state. So when I talk about that posterior distribution doesn't take into account the lack of confidence in this bias term. It's just considered a fixed term. It's a fixed function. It's a function of state. Okay. So what do? We calculate the posterior probability that the advantage is greater than the threshold. We take that posterior probability and we use that to randomize to send a suggestion. That's posterior sampling. So this is what the software is doing online as the study goes on. In terms of the learning algorithm, I'll just give you a highlight on the learning algorithm and then I'll give you a highlight on the posterior sampling. So in particular, when I said we used a Bayesian linear regression, in actuality, we used Bayesian linear regression on the advantage of sending a suggestion versus not. Okay, so you can see it's a very low dimensional model. Theta is only 5. It's a linear model, only 5-dimensional. Theta is 5-dimensional. This is a very high noise setting, and this is one of the reasons why we use such a low dimensional model for this advantage of sending a suggestion versus not. We knew it was a high noise setting, So we wanted to bring in prior information from Hartstepp's V1. And we did that through the prior. So we use an informative prior in this study. It's a Gaussian prior on theta, the 5-dimensional theta. I'll show you what the features are later, okay? Both the mean and the variance were based on data from Hartstepp's V1. And then what happened is you form one prior for everyone in your study. Then each individual in the study went through a week where they were randomized to get a suggestion or not, just with a constant probability, and that prior was then updated for that individual. So by the end of the first week, everyone has a slightly different prior, the posterior. See if there's anything else I want to say. Oh, yes. So a really important thing to mention is that informative prior. So I said that theta is 5-dimensional. The first entry in theta is all the features are standardized. So the first entry in theta is the overall sort of average effect of the intervention, sending the suggestion versus not. In Hartstepp's V1, there was enormous amount of evidence that sending a suggestion on average was better in terms of physical activity than not sending a suggestion. So the prior mean for the first entry in theta is positive. This is going to be really important. It's going to come up again later in the talk. All of the other prior means for the remaining 4 entries are 0. They're all 0. Okay, so now to the action selection, a highlight. We had actually adapted the algorithm in a number of ways, but I'm giving you the highlights that we can move to the evaluation part. So in terms of the action selection strategy, here at the very top, I just reiterated what I meant by posterior sampling. So you calculate that posterior probability, the advantage is greater than threshold, and you use that posterior probability to do your randomization, to do the select, to send a suggestion. So this is sort of an embarrassing thing. I didn't really know what I was doing. It's pretty clear. We started this study. We started with, you always run these studies with a pilot group of people first, and then you go into the real field and you look at the pilot people, because there's all kinds of bugs in the code. So what happened was in some states, the posterior, since we're in a Gaussian world, Gaussian prior, Gaussian model, the posterior distribution you write down is Gaussian. So in some states, the posterior distribution of the advantage minus the threshold is going to center at 0. What's that doing? It's indicating that there's not enough data evidence supporting sending a suggestion in that state. So what happens then? That posterior probability is averaging around 0.5. So that means that with probability 0.5, we're going to send that person a suggestion. This is a disaster. We have the accruing data has no evidence that that suggestion is helpful, yet we're going to send that suggestion with probability 0.5. And we know this is a world, we're experimenting on people as they go about their life. This is a world where you really don't want to send things if there's not good evidence or some minimal evidence. It's a disaster. Another thing we have to keep in mind is you want to be able to permit causal inference off policy learning after the study's over. So suppose I'm in a particular state, the posterior probability that the advantage is greater than the threshold is really high, indicating a lot of evidence that in that state it is really worth it to send a suggestion. In fact, the posterior probability is so high, it's like 0.95 or 0.99. What's going to happen? It's a disaster if you want to do causal inferences after the study. Because once you send a suggestion, almost always in a particular state, you can never unlearn that it wasn't, that on average, or it's not good to send that suggestion. So we have to be careful about that. I didn't realize any of this, okay? We ran the pilot and it was just awful. I was just appalled that I hadn't realized. Okay, so what happened was, what we did was I drew this. The x-axis is the posterior probability, the probability that a suggestion is sent to the individual. So when the posterior probability is 0.8 or higher, with probability 0.8, we sent the suggestion. So in states where there's a lot of evidence, 0.8 or higher, with probability 0.8, we sent the suggestion. The software sends the suggestion. If the posterior probability is 1/2 or lower, with probability 0.2, a suggestion is sent. Now, where did 0.2 and 0.8 come from? We just didn't pull them out of thin air. 0.8 and 0.2 come from the actual domain. It was big group meetings about this. So 0.8 is a concern, you know, how many messages on average do you want to send someone if they're in if they stay in a particular state? How many times do you want to bother them if they're in that state on average per day? That's where 0.8 comes from. And then 0.2 was, even if there's not a lot of evidence that sending a suggestion in a particular state is worthwhile, it's very interesting. First of all, you have to be able to do your after study analyses, as I mentioned, but there is some health benefit of variability. If you're familiar with psychology, you know that variable reinforcement, variable schedules reduce the rate of habituation. So we decided, okay, 20% of the time we'd send it, even if there was not a lot of evidence. Oh, I'm supposed to pause for a clarifying question. So
How sophisticated is the capture of the state? Because as I was thinking in my mind, I'm thinking, oh, the state is, am I getting into a shopping mall and therefore receiving the, you should maybe walk. I mean, so yeah, what was the state for you guys? How much differentiation you could do?
Right, so the actual amount of state data was overwhelming, massive amount of data. You know, how much are you using the app? Where are you? Your prior pattern, how you got to where you are right now, how busy you can imagine how busy your Google Calendar was. So this is just, I mean, this high noise setting, this is a problem because you want to extract signals. So with V1, we went and looked at the data and we looked at what features or summaries. So you have to construct the state. Okay, so I'm using state in two different ways. There's state in what data I have collected recently, and there's the construction of a state. So you have approximately something like a Markovian or bandit type environment. And that's what I'm talking about, the latter. So we constructed a state from Hartsev's V1, and we added some things we didn't collect in Hartsev's V1 that the scientists wanted to collect here, and they thought would determine whether or not it's useful to send a suggestion. So we added those. So we ended up with, I guess the total number of state features was, I think 10, only 4 of which appear in this advantage term.
Thank you, that helped.
Yeah.
So, on average, how many cases did the algorithm have in order to learn the reward function? Because that seems to be very data intensive, right?
And this is why it was so important that we use an informative prior. So the variances on that informative prior, they give you the stickiness of the prior, right? The smaller that prior variance is, the more data you need to overcome that prior. That was one of the reasons why we wanted to use an informative prior, because we knew that high noise setting, you're not going to learn very fast. Also, this algorithm is run separately on each individual. I can tell you why when I answer questions afterwards, if you, so each person, you have 5 times a day, you have 30 times in a month, you have either 3 months or 9 months. So it's a pretty good time. It's like in the 9 months, it's like 1,300 time points per person. Yeah. I mean, it's all, this world is inherently non-stationary, right? But one hopes that the stationarity is very slowly evolving.
But is that the case when you're dealing with apps and
you're going to see, you'll see an example, because this is all part of the evaluation.
Susan, a nice question.
Yeah.
So do we watch simultaneously 1 and 0, like RS1 and RS0? So can you watch simultaneously, or you're averaging somewhere? When you're taking the difference, like no reward
Yeah, it's
function.
from this Bayesian linear regression. It calculates the posterior mean, posterior
Well, you're
distributions.
the average, but once time they take one action, right? Like,
Yeah,
zero
only
or
one action gets delivered.
okay.
Either don't send a suggestion or send a suggestion. Yeah,
But you're doing the regression too.
yeah. So what happened is every night we updated the learning algorithm, and during the day we used the action selections.
Last just a second.
Yeah.
So the last thing you said, so this is not modeled episodically at all. It's one
No,
long.
it's just one
Okay.
long.
So days and nights that don't make, they're just.
Oh, well, they're
state
part of the state. They're
Okay.
part of the baseline state.
state. Okay.
Yeah, but they didn't seem to impact they didn't interact with the treatment in the V1, so there's no reason.
Fine.
Yeah,
Thank you.
yeah. Okay. So this act of trying to developing an algorithm that attempts to maximize the reward subject to these constraints, this is personalization in some sense. And you want to ask, well, did that occur here? And here's this slide has some first questions. So this algorithm, as I said, was run separately on, there were 91 individuals in these V2 and V3. And the first question we wanted to ask was, on average, across people, these are all individuals who were newly diagnosed with stage 1 hypertension. On average, across people of that type, is there some effect of sending a suggestion versus not on their physical activity? Now, we had already developed a method for primary analyses that would be used in reporting the results of a clinical trial. That's not the method I'm going to talk about here. Here, I'm going to do all the analyses under an assumption that the environment is within a person is a banded environment. That is, the potential outcomes, the reward under action 0 and the reward under action 1, they're independent across time within a person. Now, it turns out that's not a bad approximation in this study because the reward is only the 30 minutes after a decision time, and the decision times are 2.5 hours apart. And we're going to also, so under that assumption of abandoned environment, I'm going to address these questions. Also, another one was, is the better action user specific? It's really interesting. Even in the same state, do users respond very differently? These are two of the questions we'll look at. So we were actually, like when I first, I'll show you at the very end of the talk, I'll show you the slide that motivated all of this. But we were at a loss, how to even think about these problems. It wasn't like there was a place I could go in the literature to find how to even think about this. And so after a lot of going round and round in a circle, we went to old clinical trials literature, like really old. Like this was a tutorial after the literature was pretty much developed, very mature literature in 1999. This is called old literature. And this is meta-analysis. It's not meta-learning, okay? We're not talking about meta-learning. Meta-analysis is one of the biggest tools used in today's world to combine results across clinical studies. It's used to harmonize results across countries, across states. It's one of the major tools, but it's very mature field. And what we did was we acted as if each user is so in classical meta-analysis in the clinical trials world, you have multiple clinical trials and you want to combine results across multiple clinical trials. We're going to have multiple users. Within each user, we have multiple tuples. In the classical world, you have multiple participants in every trial. So in this setting, you envision that each user has their own coefficients, these own weights. They're 5-dimensional. This is theta 0i. And you estimate each user's own weight, user i's own weight, by that user's data. And in particular, we use the posterior means for that user, the posterior mean, the 5-dimensional posterior mean. Now, from a frequentist perspective, this kind of makes sense. This is just ridge regression. That's all it is. All we did was use a ridge regression estimator for this to estimate it. So that's theta hat I is a ridge regression. It's an L2 regularized estimator. And we used this really nice tutorial. Remember theta I. So in classical meta-analysis, there's two ways people think. There are different ways of asking questions. The first way is, I'm only interested in these clinical trials in front of us. I'm only interested in these 91 users. I'm going to make statements only about these 91 users. So in this case, one assumes that approximately this ridge regression estimator has an approximate normal distribution centered at the truth with some variance, 5-dimensional covariance matrix, which you have to estimate. So you're essentially assuming something akin to a central limit theorem. And there is a central limit theorem in this setting under certain conditions. The second way to think is population-based inference. Now you think, oh, my set of clinical trials, i.e. my users, are some subset of a population of users. Now, it turns out that made a lot of sense here. This trial, as I said, was going on at Kaiser. All the patients within a certain window of time, as soon as they were diagnosed with stage 1 hypertension, they were asked, would you like to join this study? So if one got a relatively representative sample of people saying yes, you might be interested. If you were, say, for example, Kaiser, you might be interested in knowing, how would this work if I rolled this out to my patients who are newly diagnosed with stage 1 hypertension? In this case, you think you have a multi-level type framework. You think of these unknown user 5-dimensional vector has itself a normal distribution across the population of all users. Very much a hierarchical setting. Okay, so what we did is we looked at that tutorial. We took the methods from that tutorial. So I want to explain what this test statistic is. First, E is a one-hot vector. All it's used to do is to pick out each of the entries in the 5-dimensional theta vector. That's all it's used to do. So it just picks out each of the rows so I can look at each row separately. That's all. And what we do is, so we pick out a row in that top, and then we calculate a weighted average, and we use that to center our confidence interval. This weighted average of the user theta i's. And the weights are determined by the within user variance across time and the between user variance. This is an empirical Bayes estimator. And from that, you deduce a confidence, you assume it's you have this normal asymptotic normal distribution, and you form a confidence interval. At first, we were pretty excited when we saw this, because in that first row, you see, well, the confidence interval is away from 0. It looks like, on average, just like Harstett's V1, it looks like we're seeing an impact, setting a suggestion versus not. However, you go to the second row and you realize your things are not so hot, because the effect of the prior dosage here is a summary of how many messages have been sent to the user in the recent past. And the more messages that were sent, the more you get this negative coefficient. You have to multiply it to it. And that essentially kills the overall effect, unless you're in a setting where there's been very few recent messages. It's very disappointing. The other features were recent engagement with the app, looking at the app of your own volition. This feature was location, whether you were in a structured environment or not at the time. And this feature, we really had a lot of hope for it. It didn't pan out. This is how variable your step count was at that time over the past week. A lot of variance. You might have more room in your day to change your behavior, less variance, less so, but it didn't pan out. So this is seemed very negative. And in fact, this next slide emphasizes that. This is population-based inference. So we're in this state of average dosage, the state of having average number of suggestions, recent suggestions. The users engaged, they're at home or work, that's a structured environment, and the recent variability and activity is low. We form that confidence interval using the prior slide, and indeed, you see exactly what I said in words to you before. doesn't look so great. So this is all population-based inference. This is all an average across population, people with stage 1 hypertension. So then you ask, well, is the better action user specific? Is there any evidence of this? So again, we use this E, the one hot vector, to pick out each of the entries. Remember, theta has 5, is a 5-dimensional vector, and we form a chi-squared statistic. We look at the entry for each individual minus the average over the individuals. That's a weighted average. Take the square and then weight that, and you compare that to a chi-squared on 90 degrees of freedom. This is extremely classical inference. It comes straight out of this tutorial. So the null hypothesis is a hypothesis testing setting, and it's finite sample inference about these 91 users. The null hypothesis is that all of the users have the exact same theta weights. So each weight, there's 5 weights. Each one is listed here in turn, and it's pretty clear there's a lot of heterogeneity in effect. The interesting thing is this heterogeneity is not reflective of the states these individuals find themselves in. It's not reflective of that at all. So the next thing we did was we looked at, suppose we start to compare and look for heterogeneity or an average effect, where you take into account the states that individuals find themselves in. So on average, does the bandit algorithm select more effective actions than the prior? Remember, the prior was gun-ho on these messages, send the suggestion at the population level. So here what we're going to do is we're going to estimate the average reward for policy pi. So this average is an average over the state distribution, as well as any stochasticity in the policy. And remember, we're talking about posterior sampling, so this has stochasticity in it. We use really simple estimators. One could use more sophisticated estimators here. So the estimator, the user's average reward under the learning algorithm, the bandit algorithm, is just the average, the observed average for that user. And then the estimator, the average reward under the algorithm according to the policy, the prior distribution, the policy according to the prior distribution, is just using importance weights. So this is not a doubly robust estimator if you're familiar with policy learning, it's just using the importance weights. Now the theta is 1-dimensional, it's not 5-dimensional anymore. You have the exact same parallel structure to what we looked at before. Before we were looking at regression weights, now we're looking at the off-policy value. Here we act as if each of the difference between the estimated values is approximately normal, and then that's at the user level, and then across users you get this normal distribution across users. So we ask the exact same questions. So now we're taking into account the state distribution compared to the last 2 questions. Does the bandit algorithm result in higher average rewards than the prior? This population level inference. And in fact, there is a little evidence, and this is probably because the prior wanted to send suggestions all the time. And then we asked, does the average reward vary between the bandit algorithm and the prior? Does the difference between the difference between the bandit algorithm and the prior, is it the same regardless of what user you're talking about? Are they always the same? The advantage of using the bandit algorithm over the prior, is it the same regardless of the user? And here you see there was gross heterogeneity, indicating that some users probably benefited a lot, some users did not. So now I'm getting closer to what motivated this entire, it's this question that really motivates this entire talk, but we'll do this one first. So on average, across users, does it appear that the bandit algorithm learned over time? We know that the prior is wrong, at least at the population level. It was wrong. We've seen multiple, I've given you multiple analyses of why it didn't. on average across the population, sending a suggestion is not better than not sending a suggestion. So does the bandit algorithm on average across the people learn this? More importantly, how fast does it learn this? Okay, so what we did was we used Bootstrap to do this. So this blue curve is the real data. The blue curve is the average posterior mean of the treatment effect in this particular state. So the second bullet point is the state we're talking about. It's the exact same state we saw earlier in the top. The blue curve, I'm not sure if you can see it, but it starts out at 0.47. That's the prior mean overall effect of sending a suggestion versus not. This is day in the study on the x-axis, and y is the posterior mean of the target state. That's the target state up here. And it started out at 0.47 because that's what the prior mean for the overall average effect was. See, that blue curve goes down pretty fast. Decreases pretty fast. So what are the black curves? There's 2,000 black curves. So what we did was we used ideas from regression in Bootstrap. So what does one do when you use bootstrapping for regression? What you usually do is you create residuals. You keep your covariates, you create residuals, and you bootstrap the covariate residual pairs. So what we did here was for every user, we had their state at each time, and we created a residual. We subtracted from the reward the expected mean reward according to the posterior distribution at the end of the study. We created a residual. So each individual has state residual, state residual, state residual for the entire duration of the study. All 91 individuals have this trajectory, state residual, state residual, state residual. Then we collect a bootstrap sample of these, of 91 users, sample with replacement from these trajectories. We end up with 91 series, state residual, state residual, state residual. And we run the bandit algorithm individually on each one of these bootstrapped individuals. If the bandit algorithm chooses don't send a suggestion, we add back in the mean reward function under don't send a suggestion. If the bandit algorithm suggests send a suggestion, we add back in the mean under the prior treatment effect. So we act as if the prior is correct. So each one of the 2,000 curves is from a bootstrap trial under the ground truth that the prior is correct. So already you see that in our study, we deviate from that ground truth really fast. Within about 30 days or so, the average, it's clear the algorithm has learned that the prior is completely wrong. So here's another way to, so here we did the exact same thing, but now each one of the black curves is under the ground truth that the posterior treatment effect is true. Here, it makes perfect sense. The blue curve stays well within the mass. So this is like a face validity. Does anybody have any questions right now? I'm not sure if I did a good job explaining this. No questions? I'll let you cognate on that. Okay, so let me, so this is a way to think about whether or not, so I would say that this generalization of a bandit algorithm, it learned extremely fast on average across users because it deviates very quickly from what you would expect if the ground truth was that the prior was correct. Okay, so here comes the next, the last question. And we had a number of users that if you looked at their data, it was glorious. Here's one such user. The horizontal axis is the day in the study. This user, this is going on in Seattle. This user came into the study in mid-November 2019. and left the study beginning of August 2020. This is when Seattle shut down because of the beginning of the pandemic. The y-axis is the posterior mean of the treatment effect divided by the posterior standard deviation of the treatment effect in that user's current state on that day. So the state is evolving, right? It's this particular user's state on that day. So when that ratio is high, that indicates the algorithm is saying it expects that sending a suggestion is better than not, because the posterior mean is higher than 0. And that directly translates into the posterior sampling probability being larger. When the value is below 0, of course, the posterior sampling probability is low. So if you look at this, what we did was we color-coded these. The blue dots are when the user was recently engaged of their own volition in the app. And that's whether they were yesterday they were engaged in the app. And the red dots were if they weren't that engaged in the app the prior day. And you look at that, I looked at this, my collaborators looked at this, we thought, this is fantastic. We're going to get 1 million NIH grants. We're going to be able to sell this software to everyone under the sun because we are personalizing. We're so cool. And then you think, you got to be a statistician here, and you think, well, we know with runs of random numbers, you can get a run of ones just by chance, right? So is this all, is this run of blue dots being higher than red dots, is this just chance? We got to do truth in advertising here. It's terrible. I had these big hopes of all these NIH grants just streaming in. Okay, so what we did was we did another Bootstrap study. Now we do it for this one user. Remember, from one user, each one of their tuples, we create state residual, state residual, state residual. So now we can do Bootstrap samples of the state residuals. Okay, so let's just go slowly through this. So the blue line is the actual posterior mean for the interaction effect of treatment. And it starts at 0 because the posterior mean of engagement, the weight for engagement, what the prior mean for the weight of engagement was in fact 0. Engagement was a new feature in this study. So we started it with a prior mean of 0. So you see the blue curve. Each black curve is a Bootstrap version of that individual under the ground truth of no effective engagement. Okay. No effective engagement. The blue curve here, which is the real data, is completely within the mass of black curves early on. Go back to that prior thing. It looks glorious here. I thought, man, by January, everything is pretty clear that you should send a suggestion when they're engaged and don't send one. This could have happened easily if there was no effective engagement. It's well within the mass. Only when you get out into June do you see that the blue curve has drifted above the mass, indicating, yes, there's some signal here that the algorithm is really working. This is sort of related to the question in the back, when do you really get enough evidence? So it was only by the time we got out in this period that there was enough evidence. And then the study stopped. So I'm not sure if this blue curve would have gone back up. We don't know. So we used a sequential decision-making algorithm to personalize. But did we achieve personalized digital health? We assumed each user is a clinical trial to do these analyses, right? By that I meant a clinical trial in quotes, that is, the potential outcomes under getting a suggestion versus not are independent across time within a user. How would you do a better job of assessing personalized decision-making, even if you're okay with this assumption? How would you do a better job? How would you address personalization if this assumption is violated? Say you have autocorrelation within across time within a user. How would you assess this? Right now, there's not anything there. It's completely open. How would you do a better job under both of these settings? Okay, thanks. That's the end of the talk.
The questions for Dr. Murphy?
Somebody must be totally confused enough to ask a question. Yeah.
I am totally confused, so it's something unrelated. I'm thinking about rewards to the users. What is the reward to the user for engaging in that activity? Because there is no immediate reward. The reward comes after months.
Right, so there were a lot of intervention components in this app. Actually, we had 2 algorithms running. There was another intervention component. We had a different algorithm running, and there were 4 more intervention components that we were micro-randomizing. So this is a big factorial design. And part of, then there were base components that everybody got, they didn't get randomized to. And one of the base components is they could track their behavior over time. So these people just got a shock to their system. Remember, they just learned they've been diagnosed with stage. Well, let me tell you about stage 1 hypertension. You just get diagnosed with stage 1 hypertension. If you're successful about changing your behavior and becoming more physically active, you have a good chance of never having to go on drugs. So it's kind of a unique time in your life to try and be physically active. Now, there's no guarantee that you won't progress and have to go on hypertensives, but there's a good chance that you won't if you can change your behavior. So that just happened, and they came into the study. So people were pretty engaged. And for whatever reason, COVID didn't seem to cause a problem with this. Maybe it's because they had nothing else going on in their life. I don't know. So they're getting a lot of feedback from the other components. They're getting to track. The whole user interface is pretty sophisticated. They could track. I actually have tons of slides from the user interface. So they get a lot. This is just one component. Yeah.
So how much in that setting then gets a little bit confounded by, I assume that they also get diet recommendations to try to adjust their blood pressure, and then how often are they checking their blood pressure as a reward mechanism throughout?
Right. Yeah. So this is like a factorial design. There's this balance across levels of the factorial design. And so you ask questions. This is a setting in which, so the composition of those who got treated and those who didn't, the composition in terms of these other factors is approximately balanced. That's the whole idea. I mean, that is the power of the factorials. Yeah.
So how could you possibly learn to transfer what you learned from this population to another population? So you don't start from scratch every time. Have you thought about doing something like phenotype analysis, trying to find out clusters of users that would have unique priors so that you can get
Right.
quick start?
Yeah, so we have 2 options. We can form another global prior, an updated global prior, or we can look for clusters of users. We haven't done that, but that's on, like we just got the data recently. But one of our goals is to look to see if we have clusters of users, and then we can form a prior for each of the clusters. The study actually, the study team got another grant right when we finished this. And so they just continue, and this is for people in Southern California who have obesity, and they're using the exact same algorithm again, but with other factors. So when that study's over, that study's still in the field. When that study's over, we'll have 2 different populations in which the same algorithm on this component was run. So that'll be interesting to see if we have similar types of results.
The online trials currently is pretty difficult to organize and expensive. I know that you have done some exciting work on policy learning in the context of mobile health data. So, how does that kind of fit into the policy analysis? Is there a way to combine both policy evaluations with this online learning? Question number one. I have another question related to the previous question. You talked about meta-analysis. There's a lot of recent work on meta-reinforcement learning, meta-learning. How does that apply to?
Yeah, okay, so those are great questions. Let me just talk about the first one first.
Policy evaluation.
Yeah, thank you. Okay, so where are we going? So this is true. So so I'm just going to tell you what my dream is. So like when, say, Kaiser, was run at Kaiser, when Kaiser rolls out their app for their individual stage 1 hypertension, that app has multiple intervention components, right? It has one about activity suggestions, it has one with food, stress reduction, so on. My goal is that another component is going to be an algorithm. And this algorithm will be constantly updating the selection, when to send messages and when not. Now, in any kind of implementation of a digital health application, you don't just say, oh, I'm going to implement this and walk off. You have to have a whole monitoring schedule, because if the operating systems are updated, the app breaks. I mean, there's a whole sense of responsibility that goes when you roll out an app like this. So a natural thing to do is to have intermittent batch analyses, where you take the existing data and you do off-policy learning and other types of causal inferences. And this is like a hierarchical RL. And there are certain red flags are monitored. In the industrial setting, this is like monitoring an industrial process. And so if there's a certain number of red flags, staff may be called in. Maybe some patients, their behavior seems really poor. So there'll be a number of hand-tuned red flags, but then there'll be some red flags that will come about from an off-policy analysis every 3 or so, a certain number of months when you have a batch of data. And that will be used in a systematic way to suggest ideas for how you should change the algorithm. And the extent to how much that becomes automated is a question one needs to address. But that's where I see this all going, is you want to learn both within a study, but you want to learn between studies. And this whole business of regret minimization, I think this is completely bogus. Because that's a setting where you're saying, I don't have to ever learn between studies. And even in ad placement, we want to learn between studies. Your second question.
What's on meta-learning?
Meta-learning. Okay, so it's here we ran this algorithm on. We had 91 tasks, right? Potentially very different 91 users. Potentially, maybe if we get to cluster them, we can have fewer clusters. So let's just say at the beginning 91 tasks, and we want to learn reasonable action selection on all 91 tasks. And here we didn't pool any information. I think I'm answering your question. We didn't pool any information across users. Why didn't we? Let's go to, we have to learn after the study's over. Let's go to off-policy learning. What are they assuming? That the users are completely independent, right? The units are completely, like if you go to off-policy learning in education, in online education, it's the users are all independent. Our users, if we pull information across the users, they're not independent anymore. And for our primary analysis, which I didn't tell you about here, it has to be extremely robust to all kinds of assumptions, because it's going to be used to justify the clinical trial, the funding of the clinical trial, the sample size. So at the time we developed this trial, we didn't know how you would do a primary analysis if you pool across users, because now you don't have 91 users, you don't have 91 independent sources of data. If you pool information in order to choose their treatments during the study, that is, if you do some sort of even partial pooling, we didn't have any idea. Right now, we have another trial that's going into the field in it's in oral health, helping people with poor dental health. It turns out bad dental health is related to cardiovascular disease. So these are individuals that sort of can view it as a prevention to help people prevent heart disease. Anyway, in that study, we're very concerned about noise. We really want to pool over the users. And I think our goal is that we will have a primary analysis that will allow for pooling over the users. It depends. I'm pretty sure we're going to have it. And then we'll be able, in that study, we'll do complete pooling. We have to be extremely conservative because everyone on the team, remember, I cannot harm anybody on that team. All of us have to come together. It takes us like 5 years to get these grants. It takes us about 2 years to get the grant. It takes about 5 years to run the grant. Everything I do has to be part of the team. So I think we're going to end up being able to completely pool in this study. It's going to be really interesting because, you know, the analyses are completely different from, it's just going to be really interesting.
Following his question.
Yeah.
So when you're doing this Bayes method, there are some population level parameters like hyperparameters, right? So when you get this individual posterior, you can approximate possibly some of the parameters. Don't they tell you if some individuals are like outliers, like they need much more treatment than others because they know the population?
Right.
level?
This is part of the whole idea of continual learning between the studies. You're going to want to see if there's certain individuals whose whole pattern just doesn't look right, and maybe they need to be contacted by the staff. So you want some automated way to track people, and you'll also be correcting, you know, the fact that
because the states usually should explain that because you have a lot of states, but possibly there are some missing states, and that's why some individuals
are states that are just not observed, right? And you have no idea, but then you can always remember, this is in a setting in which you can contact individuals and ask them how things are going.
But there is no question of state selection, right? Because you have a lot of states and you don't learn about them that, you know, in future trial or future.
Yeah, so now when we analyze this data, and we're thinking, we're already writing a grant proposal for a future iteration of heart steps. We'll have to redo the policy. We're going to ask what features are important. A lot of the features we thought were important didn't turn out, but some did. Dosage we thought would be very important, and it was indeed extremely important. You know, so that we'll iterate. Yeah, engagement will probably stay in, and probably also some other variation will probably stay in because we're seeing some users where variation related to. Yeah.
So going back to that question of the features, have you done ecological momentary assessment studies or surveys or focus groups to try and understand what are the triggers for somebody, what are the features of a state that are important so that you can measure those in the study?
Right. So I can tell you what we did do. In Heart Steps V1, we had EMA, that is self-report every evening, and it concerned whether or not they perceived the intervention as burdensome and why. And we also did qualitative analyses. We interviewed a group of people after the study was over, and in fact, we had noticed that in V1 that the treatment effect deteriorated with time. We thought it was due to burden, but in those qualitative analyses, it was pretty clear that people felt very engaged with the app, the overall app, but they just didn't see the suggestions after a while. So the thought is that this is mainly, this deterioration with dosage is signaling habituation. And that's coming straight from the qualitative analyses. It's not coming from the data. You asked, so there were other quality, I have to be honest, I'm not that good of a person because I wasn't part of the qualitative analysis team. And with this study, I was asked to give them a list of 10 users to go and give them questions to ask those users. So I picked 5 users who had beautiful patterns and 5 users who things just seemed to go to hell in a handbasket. And I had a bunch of questions, and I haven't gotten that data yet.
So Susan, I have sort of a silly question. Maybe you addressed it at the beginning. So how much information loss is there by assigning the treatments sort of adaptively the way you do?
Yeah, so it depends on what your goal is, right? So if your goal is to assess whether or not, on average, across users and across time, whether or not there's an effect or not, you might think, well, I should compare the information to address that question if the randomization is done using a banded algorithm versus the randomization is like 0.5, you might think. I mean, that would be the natural thing, right? The problem is, in this setting, that question doesn't make a lot of sense. Why? Because the burden, that people just will drop out if you send them too many messages. They delete the app. They stop wearing the tracker. So so what you could do, you have to find a comparison randomization scheme which would be tenable in some sense. And what in that first week in which we did straight up randomization, there the team, not me, I wasn't asked. I would have asked for a little bit more, but I must have not been paying attention or something. But the team decided to randomize with probability 0.25 to a suggestion. So that would be the comparison. And I think we got more information here than that. Do you see the point? I didn't do an analysis, but 0.25 is a very low probability of getting a suggestion. Much lower. Remember, our lowest probability we can have is 0.2.
But you didn't really learn about that lowest probability.
No, it was decided by the team. But how did they decide that? They were worried about burden. They were worried you would be sending too many suggestions at a bad time. And when they're deciding that 0.25, they're thinking, well, let's think of the state in which person would not like to get a message. How often should we send a message in that state? This is what they're thinking in their mind. So it's not the normal randomized trial kind of setting. You know what I mean? It's just not. Yeah.
And I guess there was nothing in the model that allowed you to adjust according to whether they had responded to previous suggestions subsequent times.
Well, the Bayesian analysis, of course, if they responded at the prior time, and that was when they got a suggestion, that contributes to the posterior mean, right? And that influences the randomization probability. Because remember, we're tracking the posterior mean treatment effect. So that's a contrast between getting a suggestion versus not.
But there was no, like, getting 2 or 3 sequential suggestions.
That was the dosage. And remember, there was that big negative coefficient of dosage.
Right.
Yeah.
Okay.
Yeah. And that deemed it. That would the higher the dosage was, the lower the probability we get. Yeah. Yeah.
Any other questions? Well, let's thanks Susan for her